All right, in this lecture, we're going to talk about nonlinear root finding, or specifically nonlinear root finding for a single equation with a single unknown. We'll talk about systems of nonlinear equations in a different lecture. So we're going to give an overview of several common methods. The first method is the bisection method, and it's probably the simplest method. I think the easiest way to explain it is with this simple animation here. So we have a function. Obviously, the root is right there between 0.75 and 1. And what we're going to do is pick two initial guesses that bound the root, right? So the guess A0 must be on the left side of the root. The guess B0 must be on the right side of the root. And if we do that, then we can simply bisect that, find a new point we'll call P0, and then what we'll do is evaluate the sign of, compare the sign of P0, A0, and B0. And what we're looking for is them to have opposite signs. So if we evaluate the function at P0, you can see it's a positive number. Same thing with A0. If we evaluate the function there, it's a positive number. So in this case, those two are positive, whereas if we evaluate the function at B0, that's negative. And therefore, we know that A and P are on the same side of the root, and that's the opposite side of B. So what we're going to do is we're going to accept P as our new A and continue the process. So again, I think the best thing is just to step through this. So we're going to accept P as our new A. So now we have an A1 and a B1. This is the second iteration. We're going to bisect that, evaluate the sign, and in this case we'll accept B1. We'll accept P1 to become our B2, and so on. So we'll just continue it until we get close to the root. So I'll go ahead and just play this one time through. So the nice thing about the bisection method is that it is guaranteed to converge as long as the root is bounded by the initial guesses. So as long as the initial guesses do encapture the root, then this will always converge. So here's the pseudocode for that. Again, it's fairly straightforward. We just take an initial functional evaluation of A, and then choose a new point P to be halfway between A and B, do the functional evaluation of P, and then we have a break condition. So if the functional evaluation is exactly 0, which for floating point operations would rarely be the case, or if it's below some tolerance, then we'll end the program. Otherwise, we evaluate the sign and then choose either A or B to be the new P and continue. So there's several stop conditions we talked about. One being that we could either check to see if the functional evaluation at the point P is identically 0, or check that the bisection itself, so the B minus A divided by 2 is less than some tolerance. Other things we could look at would be, for example, if the absolute change from one iteration to the next of the value P could be less than some tolerance, or we could normalize it by the current value of P, or we could just say that the functional evaluation of P, we know for floating point operations it's unlikely that it's ever going to be identically 0, but if it's less than some very small number, then we can assume that it's close enough to 0, the absolute value of that, and therefore we can continue. So those are some other stop conditions we could use. We'll talk about these in the context of bisection method, but these are the same kinds of stop conditions that can be used in other methods. Convergence of the bisection method is on the order of 1 over 2 to the n. So basically you're going to have the nth iteration of a root where the actual root is p is going to have some error that's on the order of, some constant times 1 over 2 to the n. So we'll look at another method that has a much better convergence rate, and that's Newton's method, or sometimes called Newton-Raphson. And so for this guy, you're going to have a general function or a general formula where the new, the value of x, which is the root at n plus 1, is equal to x at n minus the function of x over the derivative of the function of x evaluated at n. Now you notice that here we require not only the function but its derivative. So therefore we need to know the derivative analytically. So here's an example just in Python where the function is x squared minus 25. Of course we know the root here is identically 5, right? So 5 squared would be 25. 25 minus 25 would be 0. So we're going to go ahead and use Python, create some anonymous functions. So here's the original function, and then of course the derivative of this function is simply 2x. So there we have f and f prime, and we'll just take an initial guess to be 6 and do it one iteration. So we can see it in one iteration it's come very close to the root, and here's what Newton's method is doing. It's taking the original function, in this case is the black line. We take an initial guess at the point 6, and we compute the derivative, which is this tangent line. Okay, so the tangent line is in red there, and then since this is just a straight line, we can evaluate the root of it algebraically, and it becomes 5.08. So if we were to continue this up to some stop condition, again we can use one like this. It just looks at the change in root. The absolute value of the change in the root must be less than some tolerance. Then we can continue this, and I'll go ahead and just play the animation here. You'll see that we start with initial guess P0. It's going to evaluate the tangent line. The root of this tangent line will become the new guess. We'll evaluate a new tangent line there. The root of that will become the new guess, new tangent line, and you see how it quickly hones in on the root. So here's the pseudocode, quite simple. We just have a loop that goes for so many iterations. Here's the formula, stop condition, and the rest is just incrementing iterations and accepting the new root if the stop condition is not met. Convergence rate of Newton's method, we can look at if we assume that we have an iteration k that's converging to a root x star with some small number, some error epsilon k, well then we can Taylor expand this about the point x star, and we get this guy, which we can also, if x star is a root, well we know that the function of x star is 0, so that simplifies to this. Then we rearrange and take the derivative of both sides with respect to epsilon k. We have this, but epsilon k we can define as this, or epsilon k plus 1 is just the difference between the roots, the error rather. The difference in the error is going to be equivalent to the difference in the roots, and so then we have this equation, which we can then rearrange like this, and then plug in our definition from the Taylor expansion above, do some simplifications, and ultimately we end up with this down here, which basically says that the error at any iteration k to the squared power times some constant out in front. So what this means is, for Newton's iteration, it converges quadratically. That is, the error will be cut in half every time we take a step. So it's very fast convergence. And it's one of the reasons we like Newton's method for these kinds of problems. Sometimes the function derivative can be very difficult to compute, or possibly we don't have an analytic function. In that case, we can use something called the secant method. So the secant method just uses the definition of a derivative without actually taking this limit, right? So this is the definition of a derivative, but we're not actually going to compute the limit. We'll use the discrete points, okay? And so with that, we have to have two initial guesses so that we can basically approximate the derivative, in this case, the red line, the tangent line. And what we'll do, use this tangent line again to algebraically compute the new guess. There, use that point to compute a new tangent line, compute the new guess, compute a new tangent line, and we continue to do this until it converges to the root. In that example, I used initial guesses that bound the root, but that's not a requirement of secant method. So in this example, I used two initial guesses that do not bound the root, and you'll see that it still converges. Again, pseudocode for the secant method, pretty straightforward. We have a couple of functional evaluations so that we can compute the derivative. A loop, computing the new point from the definition of the derivative. I have a stop condition, and then just increments and new functional evaluation updates. Convergence rate of the secant method is on the order of epsilon k to the alpha power, where alpha is this golden ratio, so 1.6. That's a little bit less than the Newton's method, and that's because the secant method doesn't have as good an approximation of the derivative. Of course, Newton's method, the derivative must be analytically calculated. So then there are hybrid methods. I don't have any actual slides to present these, but basically they're just combinations of the other ones. And typically it's a combination of the bisection method. A couple of iterations of the bisection method will produce a really good estimate for Newton's method or the secant method. And so then it just depends on if you have an analytic derivative of the function or not. So often we will start with the bisection method, take a couple of iterations to get a good estimate that will then feed into Newton's method or the secant method to produce the root. And most of your packaged root solvers, like the ones in SciPy and other places, use some form of this. Often a common form is called Brent's method, which again takes first the bisection method and then the secant method after that.